Hello, I'm Jong-Hyeok Yoon. It is my honor to present a ternary-weight compute in-memory RRAM macro with write verification, which is joint work with TSMC. This is my bio. I was a postdoctoral fellow at Georgia Tech while conducting this research, and I'm currently an assistant professor at DGIST. I received the PhD degree at KAIST in 2018. My research interest includes compute in-memory architectures, neuromorphic systems, and wireline communications. I will begin the presentation with the motivation of this work. Then I will discuss the architecture for ternary-weight CIM RRAM macro. The measurement results will be shown, and I will summarize the presentation with conclusions. A compute in-memory architecture has gained importance in achieving high throughput, low latency AI systems. A traditional von Neumann architecture suffers from the latency and power dissipation incurred by massive data transfer. Thus, CIM architecture has emerged to surmount the aforementioned problems by conducting computation in memory. By employing CIM architectures, low latency, energy efficient computing systems can be realized. CIM architectures provide high energy efficiency to light AI systems such as edge intelligence. In case all the weight can be loaded on the memory, CIM architecture renders ultra-low power consumption. However, advanced AI systems have complex network architectures where the number of weights is tremendous. Thus, AI systems inevitably employ off-chip memory. The off-chip memory stores the input and weight of AI systems in addition to the intermediate output, which is the result of CIM operation. The data transfer between on-die and off-chip memory introduces prohibitive power consumption and latency to the system. Especially, the intermediate output is frequently stored in off-chip memory, degrading the energy efficiency of systems. A higher capacity of on-die memory using multi-bit encoding can decrease the number of data transfers. Thus, CIM with multi-bit encoding attains higher system-level energy efficiency. This slide shows the candidates for on-die memory in CIM architectures. The candidate should have a high bit density and fast read speed with CMOS compatibility. RRAM has a higher cell density than SRAM since the cell size of RRAM is extremely small. In addition, RRAM can support multi-bit encoding, thereby increasing the bit density in CIM architecture. STT-MRAM also has an advantage over SRAM in the view of the cell density, but it can hardly support multi-bit encoding. Thus, RRAM is a promising candidate for CIM architectures in AI systems. In this work, we propose a ternary-weight CIM RRAM macro. There are challenges of RRAM-based ternary-weight CIM in write and read operations. The reliability of RRAM resistances hinders multi-bit encoding in an RRAM array. In multi-bit read operations, there is logic ambiguity in the current sensing map. This slide shows the challenge of ternary encoding in an RRAM array. Since RRAM has a different sensitivity to a write pulse over RRAM cells, the RRAM resistance varies over write operations. It leads to the overlap in the resistance distribution of ternary-weight RRAM cells. The overlap between adjacent distributions incurs inaccurate CIM output, thereby precluding multi-bit CIM applications. Thus, resistance calibration in write operations is imperative to attain reliable ternary-weight CIM operations. This slide shows the current sensing MAC with a ternary-weight RRAM array. The current sensing MAC is widespread in RRAM-based CIM architectures. Ternary-weight RRAM has the intermediate resistance state, which generates half the RRS current, considering the sampling margin between the RRS and HRS current. Compared to binary encoding, the ternary-weight MAC is error-prone over the number of accessed HRS cells. On the fixed ratio of the RRS current to the HRS current, erroneous MAC output is easy to occur in the ternary-weight MAC. It eventually hinders the spread of multi-bit CIM applications. To support error-free multi-bit MAC functionality, a readout circuit with no logic ambiguity should be addressed. I will show the overall architecture for Ternary-weight CIM RRAM macro. This slide shows the top block diagram of the proposed Ternary-weight CIM RRAM macro. Iterative write with verification using the ADC is employed to secure reliable resistances, thereby enabling multi-bit encoding. The proposed RRAM macro supports voltage sensing ternary-weight CIM operation. Voltage sensing read supports 8-bit-line CIM operations without logic ambiguity. I will explain iterative write with verification for ternary encoding. This slide shows the characteristic of RRAM cells in write operations. Since an RRAM array has no hard set or reset, there is a dependency upon previous resistances in write operations. Furthermore, RRAM has a different sensitivity to the write pulses over RRAM cells. Thus, a single write operation cannot guarantee a narrow distribution of RRAM resistances. To achieve reliable resistance distribution in a ternary-weight RRAM array, iterative write with verification is employed. By using the ADC, the RRAM resistance is monitored in each write operation. In case the RRAM resistance is not placed within the target range, the pulse configuration is updated, then another iteration is initiated in write operations. In the ternary encoding, the IRS resistance is placed adjacent to the RRS resistance since the resistance distribution of RRAM cells is narrow near the RRS regime. The detailed flowchart for IRS and HRS is shown in this slide. The write operation is started from the RRS cell for the narrow distribution of initial resistances. A reset pulse is applied until the RRAM resistance exceeds the lower threshold. If the resistance is over the upper threshold, a set pulse is applied to the RRAM cell. In case the RRAM resistance fluctuates over the threshold, another iteration is initiated with a lower bit-line voltage until the target resistance is achieved. This slide shows the flowchart for RRS. To set the RRAM cell to the RRS, a set pulse is applied to the HRS cell until the RRAM resistance is below the upper threshold. If the resistance is below the lower threshold, a reset pulse is applied to the RRAM cell. In case the RRAM resistance fluctuates over the threshold, another iteration is initiated. For the RRS and HRS, a simplified write process can be employed considering a single threshold. Since the RRAM cell has the upper or lower limit of resistances, a single threshold can be employed instead of two thresholds in iteration. In summary, iterative write with verification achieves the tight resistance distribution using thresholds. This slide shows the iterative write with verification in the top block diagram. During write operations, the write verification block estimates whether an RRAM cell is programmed within the target range of resistances. If the resistance is out of the target range, iterative write operation is conducted while adjusting the pulse. Then, the resistance distribution is placed within the target range and it enables ternary encoding. The next topic is voltage sensing read in ternary-weight CIM. This slide shows the structure of the bit-line for ternary-weight CIM. The proposed RRAM macro supports 3x3 corner CNN operation by accessing 9 word lines simultaneously. The ternary encoded RRAM cells has high, intermediate, and low resistance states. By aggregating the result of multiplications, the ternary-weight CIM output is determined. To obtain the ternary-weight CIM output without logic ambiguity, a voltage sensing RRAM macro is proposed. For the voltage sensing ternary-weight CIM, the nonlinearity of the readout voltage should be addressed. Since the parallel resistance drastically decreases over the number of accessed RRAM cells, a unit pair of a current source and an RRAM cell is employed, which is called the input-aware current control. Then, the readout voltage has a constant region over the number of accessed RRAM cells. However, still, there is the nonlinearity of the readout voltage over the combinations of resistances. This nonlinearity leads to the accuracy loss of CIM output, especially in multi-bit CIM operation. This slide shows the remaining nonlinearity on the input-aware current control. The nonlinearity can be estimated by using the equivalent model of the bin9. The equivalent model assumes a unique current and the equivalent resistance, which is the parallel resistance multiplied by the number of excess RRAM cells. Over the combinations of excess ternary-weight RRAM cells, the readout voltage suffers from the high nonlinearity. In the proposed RRAM macro, a feedback amplifier is employed to suppress the remaining nonlinearity. The feedback amplifier linearizes the readout voltage owing to the enhanced loop gain. In addition, the tolerance to PVAT variations is provided by controlling the bias voltage. Furthermore, the feedback amplifier helps reduce the size of the current source by adjusting the bias voltage of the current source. The detailed principle of linearizing the readout voltage was presented at IEEE this year. This slide shows the schematics of the voltage sensing bin9. The input concurrently accesses the RRAM cells in the selected bin9 to conduct ternary-weight CIM. The input-aware current control sets the amount of the bin9 current proportional to the number of excess RRAM cells. The feedback amplifier linearizes the readout voltage over the combinations of excess RRAM resistances. The proposed voltage sensing bin9 structure can be modeled as the voltage averaging circuit with HRS, IRS, and RRS readout voltage. The IRS readout voltage is placed at the middle of the HRS and RRS readout voltage. If the number of accessed HRS and RRS cells is the same, the readout voltage is placed near the IRS readout voltage. This slide shows the readout circuit in the ternary-weight CIM RRAM macro. To convert the readout voltage to the CIM output, the 4-bit ADC is used. Due to the input-aware current control, the range of the readout voltage is the same over the number of excess RRAM cells. In addition, owing to the feedback amplifier, the readout voltage is sufficiently linearized. Thus, the reference voltages are uniformly distributed without quantization to obtain the signed 4-bit CIM output. The equation shows the CIM output and the LSB voltage over the number of excess RRAM cells. The proposed ternary-weight RRAM macro has the CIM output from -9 to 9. It means saturation occurs at the 4-bit ADC output. This table shows the case of non-sparse ternary-weight CIM where RD input is high and the weight is non-zero. The CIM output under extreme non-sparsity is saturated. Considering the sparsity of the input and weight, the probability that the saturation occurs is sufficiently low, and the saturation has a negligible impact on the performance of CNNs. In summary, the readout voltage represents the combination of excess RRAM cells, and the ADC determines the CIM output with saturation. Thus, the proposed RRAM macro achieves high energy efficiency without loss of accuracy. This slide shows the voltage sensing ternary-weight CIM in the top block diagram. In CIM operations, the input is fed to the waterline decoder and the input-aware current control. The input-aware current control with a feedback amplifier linearizes the readout voltage at bin9s. Through the bin9 mux, 8 bin9s are selected for concurrent CIM operation. The linearized readout voltage is applied to the 4-bit ADC. Then, the ADC generates the CIM output with saturation. Now, I will show the measurement results of the proposed ternary-weight CIM RRAM macro. This measured result shows the voltage sensing ternary-weight CIM operation over combinations of resistances. The x-axis is the CIM output, and the y-axis is the readout voltage. Since the ternary-weight CIM can have various combinations in the same CIM output, we observed the CIM output in various weight sweep. In the first weight sweep, 9 HRS cells are programmed to IRS and LRS in turn. The first weight sweep shows that the lead-up voltage is sufficiently linearized. Even if the 0 point is placed slightly lower, ternary-weight CIM can be conducted owing to the linearized lead-up voltage. In the second sweep, 9 HRS cells are programmed to LRS directly. The lead-up voltage in the second sweep is exactly overlapped with the first sweep while showing the linearized lead-up voltage. For the last case, 6 IRS cells are programmed to LRS with 3 cells fixed to HRS. The lead-up voltage of all the sweeps is exactly overlapped with the voltage difference of 4.75 mV. It means the proposed RRAM macro provides reliable ternary-weight CIM operation. This slide shows the measured result of iterative write with verification with 100 IRS cells. The x-axis is the resistance and the y-axis is CDF. The IRS cell has a wide distribution of resistances in a single write operation. Of iterative write operations, the distribution of IRS resistances is tightened within 1 kΩ. This slide shows the LRS, IRS, and HRS resistance distribution. Considering the resistance distribution of LRS, IRS, and HRS cells, the IRS resistance is placed adjacent to the LRS resistance. However, the IRS resistance is sufficiently outside the 3 sigma window from the LRS resistance. The voltage domain in write operations is shown in this slide. During iterative write with verification, the bin9 is set to 1.5 volts, then the bin9 voltage is decreased over iterations. This measured result shows the resistance distribution of IRS cells. Since the IRS cell is susceptible to read disturb due to the absence of an upper or lower bound of resistances, the tolerance of read disturb is measured with 100 IRS cells. On the 20K read operations, the IRS cell successfully retained the resistances within 1 kΩ variation. This slide shows the measured resistance with 5 IRS cells on the 2 million read operations. This result demonstrates the IRS cell maintains the resistances even under an extreme read scenario. Thus, the proposed RRAM macro provides reliable ternary weights in CIM operations. This slide shows the estimated inference accuracy of various tasks. VGG 10 and 16 and ResNet 18 are used as a network architecture in the estimation. In the case of CIFA 100, the estimated loss of accuracy is 3%. The proposed RRAM macro helps support AI applications with less than 5% loss of accuracy. This slide shows the comparison table and Chih characteristics. We have shown the IEEE work with binary encoding this year. Here, we present unique voltage sensing ternary-weight CIM architecture with a significant increase in energy efficiency. Compared to the prior art, the voltage sensing CIM architecture supports MAC operations without logic ambiguity. The iterative write with verification provides reliable ternary encoding in an RRAM array. The proposed RRAM macro supports ternary-weight CIM operations and achieves the peak energy efficiency of 118 TOPS per watt. The test chip is fabricated in TSMC 40nm CMOS and RRAM process. In this presentation, the ternary-weight CIM RRAM macro is proposed. The iterative write with verification achieves the narrow distribution of RRAM resistances, thereby enabling multi-bit encoding. The voltage sensing CIM architecture achieves high MAC performance without logic ambiguity. The ADC with saturation attains high energy efficiency without loss of accuracy for sparse networks. The ternary encoded RRAM cells successfully retain the resistance under an extreme read scenario. The test chip achieves the peak energy efficiency of 118 TOPS per watt. Thank you for listening.